This video aims to demonstrate our IoT-based toolchain for structural health monitoring, part of the use case 8.3 within the Arrowhead Tools project. Structural health monitoring aims to give, at every moment during the life of a structure, a diagnosis of the state of the whole system by using sensors that are often heterogeneous. Our baseline scenario consists of a physical structure to monitor, an experimental 1:4 scale model bridge over which we deployed several sensors of different nature. This demo aims to tackle three main issues affecting the baseline. First, high maintenance costs, due to the lack of wireless connections and remote control, thus requiring manual work for operation and maintenance activities. 2. The presence of legacy systems to be integrated. And 3. The lack of interoperability with established IoT cloud frameworks. Over the course of the project, we implemented a number of software tools that support the engineering process of the use case both at design time and at runtime. Let us illustrate every component of the architecture. We will start with a smart sensor network, composed of low-power, lightweight, and small-footprint accelerometer sensors abstracted via the Web of Things framework. The physical layer of the monitoring network is composed of multiple peripheral sensor nodes hosting an accelerometer and permanently attached to the structure, and few cluster heads orchestrating a small subset of the sensor network. The aggregating unit is a bridge that powers up the sensor nodes and exposes them via the Web of Things interface. It is equipped with wireless connection, a battery, and a photovoltaic energy harvester. To test the sensor nodes, we're using a vibrodyne to generate vibrations over the structure. Our baseline also hosts a legacy experimental gas sensor with a LoRa transceiver by ST Microelectronics, which can provide information about the concentration of gas and different kinds of volatile organic compounds, as well as environmental parameters. We equipped the sensor with a battery and a photovoltaic energy harvester and integrated it with the Eclipse Arrowhead Framework via an Arrowhead adapter, which translates the MQTT interface of the sensor into an HTTP REST Arrowhead service following the OpenAPI specifications. To integrate the ecosystems of the Web of Things and Arrowhead, we developed the Web of Things Arrowhead enabler. On the one hand, it translates Web Things into Arrowhead services by embedding each thing description into an Arrowhead service record, creating an HTTP REST mirror. On the other hand, it translates Arrowhead services into Web Things by matching the Arrowhead service endpoint to affordances and creating a new Web Thing for each system. The local cloud gateway is the main hub for managing and exposing systems within the local cloud. It is a multi-service IoT edge gateway by Eurotech, which supports several wired and wireless connection protocols. We deployed on the local cloud gateway the Arrowhead core systems, service registry, authorization, and orchestration, where all services of the local cloud are registered. The local cloud gateway creates an Eclipse Kura bundle for each of the sensors registered and exposes them on the internet in order for them to be accessible by any cloud service. We validate our use case by collecting sensor data in the cloud and soliciting sensor readings. By turning on the vibrodyne, we inject vibrations into the structure, which are detected on the Y and Z axis of the accelerometers. By using the same cloud service, we also collect sensor data from the gas sensor. By injecting gas in the environment, we observe a subtle change in the sensor resistance, as expected. By equipping sensors with energy harvesters, we need to be able to monitor and configure them remotely. This is done via the configurator and the optimizer tools. The optimizer works both at design time and runtime. At design time, it provides the designer with an easy way to evaluate different energy harvesting solutions and different design ideas without the need for realizing and testing one or more hardware prototypes, and thus providing a turnkey solution. Depending on the available information, the user provides quantitative or qualitative estimated environmental working conditions and the estimated electrical features of the device that will be powered by the energy harvester. Once the data entry is completed, the user selects the desired solution and launches the corresponding circuit simulation. The results are available at the end of the simulation. In this example, with the provided working conditions, the selected energy harvester is not able to sustain the device, and an estimation of the battery lifetime is provided. If the results are not satisfying, the designer can start a new simulation run by changing some parameters or the harvesting circuit. In this case, only by reducing the application duty cycle, the selected solar energy harvester needs a minimum average irradiance to fully sustain the load. With any higher irradiance, it can also recharge the battery. Exploiting the same core, the optimizer can be used also at operation time to estimate battery lifetime of the system by monitoring the environmental conditions. Through the configurator, it is also able to change the duty cycle of the sensors remotely to meet certain conditions. The runtime optimizer has a web interface that allows the maintenance operator to obtain the prediction of the battery duration if the duty cycle of the accelerometer sensor nodes changes. In this example, we set the duty cycle to 50%, which is reflected by the data collected in the cloud. Due to the strong work towards integration of legacy systems in this use case, we're able to use the same tool for changing the duty cycle of heterogeneous sensors, for instance, the gas sensor. In this case, the new duty cycle is set to 10% in order for the energy harvester to be self-sufficient. This results in higher sleep time between sensor readings as reflected by the data. The monitoring of a fleet of local clouds implies the possibility to communicate with each of the local clouds on the field and to be able to send their information on a cloud platform where it can be displayed. Kura IoT Framework has the full control over the devices connected to the gateway, but it lacks the capability to monitor all the devices connected to a local cloud. We develop an Arrowhead core system called Remote Management within Kura that is specifically devoted to local cloud monitoring. Each gateway connected to a local cloud is able to visualize through Kura the services, providers and consumers of the local cloud. The second step consisted in the implementation of the new service within Kura that rules the local cloud data transfer towards Eclipse Kapua and a new section in Kapua for the visualization of the local cloud data. Each of the gateways associated to a local cloud is connected to Kapua, which now enables the monitoring of local clouds by simply selecting the desired gateway from the console. The use case evolution envisions the development of new sensing technology. To this end, we worked on the use case of a smart bolt to measure the axial load from the variation of the time of flight of an ultrasonic wave over 3 phases. First, an experimental campaign with commercial transducers and reference load cell. Second, a multi-physics simulation campaign of the sound wave propagation inside the solid domain. And finally, the validation of a piezoelectric MEMS ultrasonic transducer.